Yeah, I just introduced myself. Yes. Okay. So yes. Thanks. Okay. So yes, I'm Giulia Rubino. I work at the University of Vienna in Philipp Walter Group. And with this talk, I would like to present you some results we have obtained in our laboratories there about experimental entanglement of temporal orders. And I would also like, of course, to thank the organizers for giving me the opportunity of being here today presenting these results. So just to give you a brief outlook of my talk, I'm gonna first of all give you a motivation of why we found interesting to perform an experimental entanglement of temporal orders. Then I will explain what we actually mean by entanglement of temporal orders and superpositions of temporal orders. And then I will present you our theory-independent approach to demonstrate the existence of such entanglement in our setup. And then I will explain the experimental implementation of such theory-independent demonstration, the results we obtained, and the conclusions and outlook. So in 1935, Einstein, Podolsky, and Rosen published a paper in which they seemed to shed light on some aspect of incompleteness of the quantum theory in case someone wanted to describe it as a theory undergoing the concept of locality and realism. In 1964, Bell formulated some inequalities in order to analyze in a device-independent way this problem. By now, these inequalities have been proven on several different models, so position, momentum, spin, energy, and so on. However, there is a system in which they are never been actually applied, and this is the order between events. The reason for this is that there is no observable associated to this quantity, so how should someone apply these inequalities and even why? However, the fact that it can be done was actually pointed out already when people started to think about the fact that actually quantum mechanics predicts the existence of processes that are neither causally ordered nor a probabilistic mixture of causally ordered processes. So the idea was, okay, let's try to use this very powerful tool of the Bell inequalities to try to do a proof of existence of indefinite causal order in a way which is as much as possible device independent, if we can. And as we will see later, we do something that is slightly different from the device independent test that Bell inequalities allow. We will do a theory independent test. So let's start with all understanding what do I mean for causally ordered processes and probabilistic mixture and so on. So during my talk, I will always consider two parties, Alice and Bob, that are in two local laboratories. By local laboratories, I mean that they are closed inside their lab, and they do not really interact with the external world. They only interact with it via the state that they receive as an input and the state that they emit as an output. Okay, so supposing that I want them to operate on the same sample, on the same system, of course, they must act one after the other. So I will have that, for example, either Alice acts before Bob or Bob acts before Alice. In general, I can also have that I have a coin and I just flip this coin and with a certain probability P, Alice will act before Bob, and with another classical probability complementary 1 minus zeta, Bob will act before Alice. And this is in general what we call probabilistic mixture of causally ordered processes, where the causally ordered processes are Alice before Bob or Bob before Alice. Okay, so this was an example of, as I said, a causally ordered process. Okay. Now, suppose that I substitute this coin that I was flipping with actually a quantum system. So instead of flipping a coin, suppose that the system that I use to order, to control the order between these two states, is actually also a quantum system. So I have two quantum systems now. One which I will call target system, which was this sample that I sent to Alice and Bob, and one which I will call control system, which decides the order. So again, as before, suppose, for example, that my control system is in the state 0, then Alice will act before Bob. If it's in the state 1, then Bob will act before Alice. But, as I said, it's a quantum system now, so I can also permit quantum superposition of the two cases. So, for example, I can have a case 0 plus 1, where I will have that in a quantum superposition, Alice and Bob are acting before and after each other. This is the so-called quantum switch, and it's a process that was theoretically proven to be causally non-order. Not only theoretically proven, because actually in our laboratories in Vienna we also did an experimental test of that. And to do that we used the process matrix formalism. So we basically, just to very briefly introduce what is a process matrix, if Alice perform a measurement X, getting an outcome A, Bob a measurement Y, getting an outcome B, and the input state is Z, and the output outcome is D, I will have that the probability of obtaining A, B, and D given X, Y, and Z is given by this formula, where I have the input state, the measurement of Alice, of Bob, the detection operation, and this matrix is the so-called process matrix, which describes basically the way in which the information is transmitted between the parties. So, for example, going back to the example I was showing you before, this is example of the quantum switch. I can pretty much put a box on my input state, the measurement of Alice, the measurement of Bob, the measurement of the detection, and what the process matrix is the way in which the information is transmitted. So everything what is inside this box. And what we want to do is to observe that such process is causally non-separable, for example. So what is a causally non-separable process? As well as, for example, with the density matrix, you can define what is a separable density matrix, so what is a separable state and what is an entangled state. Here we can do the same. So referring to the case I was showing you before, I can define a separable process, a process in which with this classical probability zeta, Alice happens before Bob, and vice versa with 1 minus zeta, Bob's happens before Alice. So the example I was showing you before. Whatever is not writable in this form is going to be non-separable. So we, as a first test of causal non-separability, what we did was we pretty much, inspired by the case of the entanglement, when you have an entangled state and you want to observe whether this is separable or entangled, you can use an entanglement witness, right? So you can look at the density matrix, you can apply on this entanglement witness, and you can observe, depending on the outcome you have, whether it's entangled or separable. Here we did the same thing. So we devised a causal witness, and it's just an Hermitian operator that applied on the process matrix under study. If you get that the trace of this it's bigger or equal than 0, then you will know that the W, the process matrix, is associated to a separable process, and if you get something below 0, then it's non-separable. So what we did was simply as simple as that. We defined a causal non-separability parameter, which was just minus this value, and we performed an experiment, obtained as the outcome 0.202 plus minus 0.029, and so we showed by 7 standard deviations that our process was non-separable, causally non-separable. However, everything I said so far is very theory dependent, right? Like all the things I've said so far, I've presented you the process matrix formalism, the causal witness, and I've used this element to get the outcome I wanted to show you. So the question is, can we actually forget everything I said so far and try to have an approach which is as much as possible theory independent and show without using the elements of the theory that my process is actually a causally non-ordered process? And the answer is yes. This can be done inspired by the Bell inequalities, as I was telling you at the beginning. So the idea came from a paper which appeared in the archive last August, and it's an idea of Magdalena, Fabio, Igor, and Czaslaw. And so it's this idea of applying the Bell theorem to temporal orders to have a theory-independent proof of causal non-separability. So some days ago, someone was asking me what is the difference between device independency and theory independency. So just in a nutshell, you can consider that, so the device independency is like you have an APR source, and I mean, you can put a box around. You can be independent of this device, because if you observe some certain correlation, and once you observe this type of correlations, you will know what is inside the box. So you are device independent because you are allowed to put a box there, and depending on your correlations, you will know what is inside. In this case, when I speak about theory independence, what I say is, in our view, something that is slightly less, because you don't really put a box around your system, because we will define we will put ourselves in a general framework of a GPT, but then we will define some little ingredients for our proof. So there are some assumptions that we will do and we will then evaluate together later. And these are some ingredients that I put inside my box, and then because of this, I cannot really put a box, do a test outside and decide, okay, this was what's inside my box, because I know that there are some rules that my box, let's say, must describe. So not everything is allowed inside the box. So what are the ingredients that I was speaking about? Let's consider we are in a general probabilistic theory, and the ingredients that we want to consider so far, so we can forget everything I said so far about process matrices, causal witness, and so on. And we only have to remember now that we will consider a joint state between two parties. So before, when I introduced, I also introduced two parties before, which were Alice and Bob. But these are the two parties that are inside my switch. Now, because I want to implement a bell test with these two parties, let's consider that there are two switches. So there will be two Alices and two Bobs, and my two parties are the two switches, so S1 and S2, let's say, okay? So there is this joint state omega 1, 2 of the two parties S1 and S2. And then, of course, each, like this joint state, has the two subsystems, omega 1 and omega 2, that each subparty owns, S1 and S2. Then we will consider some maps, U, on the joint state, and some local transformations that Alice and Bob in switches 1 and Alice and Bob in switches 2 will perform locally. And then I will speak about order of operations in terms of this definite order and undefinite order of events. So now I'm gonna present you a no-go theorem, which is, so I'm gonna present some assumptions, and then I'm gonna present, based on these assumptions, a no-go theorem. And if I will be able to violate the no-go theorem, it will mean that one of the assumptions is wrong. So let's start introducing the assumptions first. So my assumptions are that the initial joint state of the target system is local. So it does not violate a Bell inequality. That the laboratory operations are represented as local transformation of the target systems. So they do not increase the amount of violation of Bell inequalities between the target systems, and that the order of operation is predefined. And the no-go theorem states that no state, set of transformation, and measurement which obey assumption 1 to 3 can result in the violation of Bell inequalities. Okay? So if I violate Bell with my state, I will know that at least one of the three assumptions is wrong. Okay, so to do this, I want to use, as I was telling you, two copies of the switch, as before. So let's go back to the switch, and let's try to understand what I plan to do now. So I was having this one copy of the switch. Let's just now produce two copies of it. So I will have two switches, and at this point I will not have only one control qubit anymore, but two. Okay, but it's exactly the same as before. So if the control qubit is in the state 0, then I'll send it to the two Alices and the two Bobs first. If it's in the state 1, I'll send it to the two Bobs and the two Alices first. Of course, as before, also quantum superposition of these two cases are allowed. So for example, I can have a quantum superposition of it sent to the two Alices and the two Bobs, and it sent to the two Bobs and the two Alices. For example, if I have as a control qubit 0, 0, minus 1, 1. And then what I will do at the end to evaluate this Bell test, I will send my target states to some parties S1 and S2 that will perform a Bell test on it, okay? So, just practical. So I will have an initial state. And this is the theoretical idea of what I want to do, and then later I will explain you the experiment, okay? So, as I was saying, for my theoretical idea, I want to devise a scheme in which I have that my target qubits are separable. So I will have, say, 0, 0. And then this superposition of the two control qubits. Okay? Then, exactly as I was saying before, if my control qubit is in the state 0, then I will have Alice and then Bob for the two switches. And if it's in the state 1, I will have Bob and then Alice for the two switches. Then I project the control qubit on the state plus minus, so I will have only these two contributions. And then I just need to do a particular choice of the two gates, of the two unitaries that I apply. And for example, I can choose the two non-commuting gates, sigma z, and identity plus I sigma x over square root of 2. This particular choice allows me to obtain the state LL minus RR, which should allow me to violate a Bell inequality. So this is what I want to do now with the experimental scheme that I will present you, okay? So going back to only one switch, what I do is I want to do it with a quantum optical experiment. So I will have mirror and single photons. And as I said, it's a quantum optical experiment, so also the unitaries of Alice and Bob must be some unitaries on some degree of freedom of photon. For example, in this case, we chose to do it on the polarization degree of freedom. As you can see, the control is the path degree of freedom. It's already pretty clear from the picture. So the unitaries that Alice and Bob are going to implement, being on the polarization degree of freedom, is just a sequence of three waveplates, a quarter and half and the quarter wave plate. And then I'm going to interfere the two paths on a final beam splitter. Then, as I was saying, we need to evaluate Bell at the end. And so I will have a tomography stage at the end. Here, I just do measurements in polarization in the standard way we do measurement in polarization, so with a sequence of two waveplates and the polarizing beam splitter. As I was saying then, we need two copies of them. We have the two parties S1 and S2. So I'm gonna produce two copies of this switch, and I'm gonna connect them to a single photon source, okay? Then I give these two copies to the two parties that are gonna implement my Bell test. And I'm gonna inject this state that I was speaking about before. So that the polarization is the target degree of freedom and the path is the control. So I will have something of the form 0, 0, minus 1, 1, as I was telling you before. So for example, we can consider the state 0, 0 to be this entry, and the state 1, 1 to be this entry. So in general, we'll send something like 0, 0, minus 1, 1. Just to give you a picture of how it actually looks in the case, in the lab for real, this is actually how it looks. But yeah, I mean, we can, it's equivalent to the other scheme I was showing you, which is a bit simpler, so we can go back to the easier scheme. So I will have this input, so 0, 0, minus 1, 1. And then it's just, it enters in this, basically, it's like two Mach Zehnder with two loops. So I will go through the first, to the first unitary first. Then I will go through the loop, and then the second unitary. Then I will reach the final beam splitter, and yeah, after interference, I will reach the tomography stage, and so the Bell stage. Okay? So let's go back to our no-go theorem, and now with the scheme I was presenting you, so the experimental setup that I just introduced you, let's see how we can evaluate the assumptions and the no-go theorem. So let's start first with the first assumption. So the initial joint state of the target system is local. So it does not violate a Bell inequality. Now, within quantum theory, it's really easy to show that a state does not violate a Bell inequality. I can simply do a state tomography. So in the case of the state I was sending inside, as I was telling you, it was the state HH. And so indeed, I obtained the state HH and the fidelity of 93.5%. So within quantum mechanics, it's really easy to show, yeah, I don't violate Bell inequalities. Now, in a theory-independent way, what I can do is I cannot use quantum mechanics, so I'm not going to do a tomography, but I can still play around with the probabilities. So what I can do is I can analyze the probabilities that I get, and I can exploit the concept of separability of a state. So the joint probability should be just the product of the two probabilities of the two subsystems. So we did this with the list of probabilities that we obtained. Yeah, as you said, it was pretty pure. It was, yeah, the state HH, as we were saying before. But in general, I observed that all the probabilities match very well with the product of the two probabilities of the two subsystems. So the separability of the state, it's demonstrated with an error of like 3%, which is compatible with this, with our experimental imperfections. Okay. Yeah, this, I mean, I don't think I need to show you that this works only in the case of a separable state. Of course, if you apply the same concept to an entangled state, it wouldn't work. For example, if I have something like HV minus BH, then I would have in the joint state a situation like this, while instead when I do the product among the probabilities, I will get something like 25% among all of them, so I wouldn't get the same outcome. This is just to show you that it wouldn't work. Okay, so assumption 1, done. Now, assumption 2, it's that the laboratory operations are represented as local transformations of the target system in the GPTs. So they do not increase the amount of violation of Bell inequalities between the target systems. Now, already with our first experiment of a quantum switch, we already showed that there is no direct coupling between control and target systems. So we already showed that we were sending different input states, and we were observing from which port the photon comes out, and the port from which it was coming out was only depending on the property of commutation and anti-commutation of the gates. So there was no direct coupling between control and target. But in general, what we could also do in the case of this situation, so a situation where I have two switches and I'm observing the mutual correlation between the two, what we did was pretty much the similar thing as the previous case. So we decided to only send the two main ingredients of our entangled state, so only 0, 0 and only 1, 1. So sending only a separable control qubit, so having a well-defined order. For example, yeah, going back in the previous case, sending only 0 and 0. And what we should obtain is that we should only get one of the two contributions of the entangled state I was showing you before. For example, if I send only 0, 0, then I'm only going to have RR. So I should obtain a separable state at the end. And so this is what you observed. We send 0, 0 only and 1, 1 only for the control qubit, and we observed the separability of the output state. So yeah, for example, in the case of RR, so in the case of 0, 0, we're supposed to obtain RR, and indeed, yes, you can see it's pretty much separable, and yeah, it's pretty much RR. And we did the same for the state LL, so sending 1, 1 for the control qubit and obtaining LL, and also in this case, the state is it's separable in terms of probabilities. Okay, so now we move to the violation of the no-go theorem. So now, instead of sending, as I just did, some separable state, I will send an entangled state. To check theory independently, just to double check that our state was entangled, I violated Bell with the control qubit at the beginning, and I obtained the value of 2.59 plus minus 0.09. So yes, it's entangled. And now I can plug it inside my entangled quantum switch, and I can observe if I get this superposition of causal orders. So within quantum theory, yes, because I did a quantum state tomography, and I see, yes, I have actually RR minus LL. So I did get what I was expecting. Outside quantum theory, as I was telling you before, I can use Bell. So I use Bell, and I violated with 2.55 plus minus 0.08. So I violated the no-go theorem. So this tells me that one of the three assumptions must be wrong. And because I proved that assumption 1 and 2 were actually verified, I can deduce that the most likely to be actually wrong in after such violation must be the third assumption. So must be the order of operation between the gates, the one that was not supported by our experimental data. A different way to see this result is as an entanglement transfer. So as I was showing you so far, if I have a state at the beginning which is separable, the control state, then I only have one order between the two possible orders, and so I'm only gonna produce one part, so only RR or only LL. Whenever instead I have an entangled state, then there is an entanglement transfer that can happen, and the way in which it happens, it's that the control qubit decides the order in which the operations are performed. The operations are performed on the target state, And so this translates into an entanglement from the control system to the order of operation of the gates to the target system. Okay? So the presence of a violation of Bell inequalities is somehow the proof of the presence of an entanglement of temporal orders. Just to double check this, we also started to insert some noise inside our setup. So for example, we decohered the control qubit inside the switch, and we simply observed that, yeah, of course, after a certain amount of decoherence, the entanglement transfer is not successful anymore. It doesn't work anymore. And yeah, after a certain limit, after a certain noise, you don't violate Bell anymore. And we did the same also with the source. So we started ruining the entanglement of our source. So sending a source which was less and less and less entangled in a control qubit. And we observed that after a certain value, we don't violate Bell anymore because there is no entanglement to transfer basically anymore. So with this, I reached a conclusion. So with this presentation, I tried to show you the experiment that we did to convince you that the indefinite causal order is something that can be implemented in a lab and can be actually also observed without requiring the use of the formalism that we have built to analyze these systems. And to do so, we devised an entangled quantum switch. And yeah, we did the first theory-independent proof of causal non-separability. So what we want to do next? So far, I only presented the interest in terms of quantum foundations. However, this type of systems has also been proved to have interesting advantages in terms of quantum communication and quantum computation. So what we plan to do next is actually to prove one of these advantages in terms of, for example, quantum communication. So yeah, with this I would like to thank you for your attention and answer questions.